Hi, linear algebra students. So in this video, which is optional to watch, by the way, I will make a very simple yet very elegant proof that the triple product between the vector u and v cross w is simply the determinant of all three, right? Taken as being columns. Before going any further, I want to say that the reason why this connection is so nice, is so deep, is because that's actually how the cross product is engineered, right? We want to engineer a vector in a way that the dot product of u with that vector will give the determinant. So for more detail, check out 3 Blue 1 Brown. He has an amazing video on that. But unfortunately, it does require a lot of detail, a good presentation, and we cannot really go into that. But what we can do is to really prove that this falls into place, right? Like, in other words, we're going to prove that formula from our definitions of the dot product and the cross product, being simply the dot product is this, the cross product is this, okay? So the idea is actually very simple. What we will do is we will replace this into that and see what happens. So, okay. So u dot, and now I will color code it, okay? So what we're replacing is v cross w. So how does that work? Well, okay. First of all, let's write this definition. So it's going to be u1, then with a plus u2. Then I'm going to give myself space, u3. And now let's just label like, okay, v cross w, component 1, v cross w, component 2, and v cross w, component 3. Okay, so let's name them like this. But obviously, as you can see, what we're going to do is we're going to replace them directly. So we have u1, and now we replace this with this. So v2, v3, w2, w3. Okay, and then don't forget the minus here, very important. So actually, I will color code it as well. So this is going to be like our -1 that pops out here times this determinant. So v1, v3, w1, w3. And then finally, we have u3, and then this determinant right here. So v1, v2, w1, and w2. Okay, now the idea is really, really simple. Okay, I will underline all of these things. Let's say in black. I think black is a good idea. So I will underline these. Okay, what I want you to guys see is that this is actually the cofactor expansion of the following determinant. Okay, so to show it to you, we're going to write u1, u2, u3 as a row. So you have like u1, u2, u3. And then the cofactor expansion goes like this, right? You have like plus, plus, minus, plus, hence the negative sign that is here, okay? And now it's going to be funny, but look, we're going to copy this down here, okay? So that you can really see, okay, that's how we got like the v2, v3, w2, w3. Now under the second, we just copy like the first column here and the third column. Oh, it matches. How amazing! So there you go. You have like v1, w1, and for the last component, let's just do a check. So this should be exactly this, and we have it. We're super happy. So it turns out that this is the determinant, right? The determinant of this guy. Now, as you can see, the vectors are right here, u, v, w, but they're written as rows. Well, we don't care because we know that the determinant of a matrix is the same as the determinant of its transpose. So let's write that down. We have, yeah, let's write that. I will stop color coding these things. Or actually, yeah, I will actually continue doing it. So I will write this in orange, let's say. So we know that the determinant of A is the same as the determinant of A transpose, which allows us to literally write the 3 by 3 determinants using our vectors as columns instead of rows. So U1, U2, U3, and then you have here V1, V2, V3, W1, W2, and W3. And as you can see, by definition, it's exactly this, right? So this is the determinant of, and again, just if I color code them just for fun, so the vector u in black and the vectors v and w in green. And this is what we wanted to prove. I hope this was nice to watch. See you in class or in the next video.